Greetings. Today I'm going to lecture on functional and requirements definition. This is an important part of the systems engineering process to define a component, system, subsystem, or even mission architecture. So let's jump right into functions. What is functions and the function definition? It is important part of the process to define and understand what it is you're designing. So it starts with the design reference missions and the concept of operations, which really helps you to flush out an understanding of the functions. And so it's this block here is what we're looking at, the functional logical decomposition. This is part of what you use to understand what you're designing. So let's talk about the definitions for a minute. So functional analysis is that process of identifying, describing, and relating the functions of a system and what the functions of a system must perform to fulfill its goals and objectives. Functional baseline is the approved configuration documentation that describes a system or top level configuration items, performance requirements. And performance requirements could be functional requirements, interoperability requirements, or interface characteristics, which we talked about previously, and the verification required to demonstrate the achievement of those specified characteristics. Functional decomposition is a subfunction under logical decomposition and design solution definition. It is the examination of a function to identify the subfunctions necessary for accomplishment of that function and functional relationships and interfaces. So here's a diagram of the functional analysis process. As we described earlier, we have the customer inputs, the needs, goals, objectives, etc. And those are come into the whole functional system analysis. So you have the requirements analysis, which, as we described earlier, analyzes the mission requirements, the functions, functional requirements, identifies and defines the performance requirements and design characteristics and constraints. The functional allocation or analysis is to decompose to lower levels of the function, keep going down further and further, breaking down that functions. Functions lead to an understanding of capability needs, and functions become part of your requirements documentation. So you allocate the performance and other limiting requirements to all functional levels. You define, refine, and integrate functional architectures. So what is functional analysis? Functional analysis is that process of identifying, describing, relating the functions that we described before. A design reference mission is a top level flow, both on the sense of functions and the design reference mission of the mission modes, as we described earlier in the development of the concept of operations. From that concept of operations and your design reference mission, you can begin to understand and translate into functional requirements. So when you see here, we have the function of the launch vehicle launching the payload from Earth to Earth orbit or to a destination. So that's its function, is basically transport of payload from Earth to orbit. And you can begin to walk through all these different mode phases and understand what is the function being performed. You haven't designed anything per se yet. You have, some diagrams of some depiction of what it might be: a lander, a interplanetary spacecraft, etc. So So decomposition is really that what you do is you take each function is identified and described in terms of inputs, outputs, and interface requirements from the top down. So the decomposed functions are recognized as part of the larger functional groupings. Functions are arranged in logical sequence so that they can be specified. Operational usage of the system can be tracked in an end-to-end path to indicate the sequential relationship of all the functions that must be accomplished by the system. So you have good traceability and understanding of these functions and their interrelationships. So functional requirements define what functions need to be done to accomplish that objectives. such as, the function of guidance, navigation, and control, the function of descent, entry, and landing, the function of mission operations of going and collecting samples. And so performance requirements define how well the system needs to perform that function. So you can see there's a difference between functional requirements and performance requirements, and that's important. So functional decomposition, the process is that you walk through the concept of operations in the design reference mission scenarios, asking these types of following questions. What functions need to be performed? Where do they need to be performed? How often do they need to be performed? Under what operational and environmental conditions and constraints? Thinking through this process often reveals additional functional requirements that you may not have considered if you had just jumped right into and started designing your architecture or your spacecraft. So here's an example of functional performance requirements. An initial functional statement: the thrust vector controller shall provide vehicle control about the pitch and yaw axis. So this statement describes a high-level function, which is vehicle control, that the system must perform. The technical team needs to transform this statement into a design to functional and performance requirements. So here's the functional requirements with associated performance requirement of that function. The TVC shall gimbal the engine a maximum of 9 degrees plus or minus 0.1 degree. Functional flow block diagrams are important to the process because it lays out an understanding of what it is that the functions are. So functional analysis can be performed in a variety of methods, and one of those is this idea of a functional flow block diagram. And I do recommend that is something that you look at and understand and use in your design process before you're even designing your spacecraft or your system. So these FFBDs define the system functions and depict them in a time sequence of functional events. So as part of the DRM, as you walk through the mission profile and scenario and the mission modes, you can then begin to have this functional flow block diagram of the what must happen, and do not assume a particular answer to how necessarily at this point. So it's what, not how at this point. The how is in the performance requirements, and they are functionally oriented, not solution oriented. So the FFBDs are made up of functional blocks, each of which represents a definitive, finite, discrete action to be accomplished, like vehicle control, or perform, an example might be perform translunar injection. So the functional architecture is developed using series of level diagrams to show the functional decomposition and display the functions in their logical sequence relationship. Diagrams are laid out so that they flow in direction, in general, from left to right. Arrows often indicated and used to indicate the functional flows. The diagrams show both input, transfer to operational orbit, and output, transfer to STS orbit, thus facilitating the definition of interfaces and control process. So as we described earlier, concept of operations and interface definition is important and part of this whole aspect of functional decomposition. Excuse me. So here is an example of functional flow block diagram. At top level, like what I showed you for the TransHab, this is not TransHab obviously, but 1.0 is ascent into orbit injection, check out and deploy, transfer to ops orbit, perform mission operations, and you also can have a contingency operation. So you can break out the blocks where you have contingencies or you have additional or other activities running in parallel. And so, and then you have, it's an or situation, it's either this or your contingency. You transfer to orbit, retrieve spacecraft, re-enter and land. So you could take each one of these and then break them down into more detail. So perform mission operations can break down to provide electric power, provide attitude stabilization, provide thermal control, provide orbit maintenance, and so on. So you can see how each one of these talks about in terms of provide something or do something. So this is an example of functional analysis for first lunar outpost, which was done obviously a long time ago, but it's a good example. You start the mission and you have two aspects of it. You perform pre-mission operations and pre-launch operations. And each one of these blocks are depicted by the shadow, which means that you can dive down into each one of these categories, these functional operations or performs, and dive down into further define or decompose those functions. So as you walk through this, you have perform Earth to orbit operations, perform Earth to orbit operations and transfer to lunar orbit, etc. Perform lunar orbit, descent and landing operations. And then you get into the or. So the and or can be used. And means you're doing things in parallel, or means you're doing one of these things. And so you could perform your surface cargo mission ops, perform your tended outpost, human tended outpost mission ops, or perform lunar sortie ops. And so you can walk through here and you basically lay out the whole mission in a functional flow block diagram of the intent of the mission of the system and what's going on, taking into account and thinking about what's going on from the human, the hardware, and the software. So this further breaks it down, and so you had your level 1 example, which shows the functional flow block diagram at a high level, and then you show level 2. You're breaking down this item number 3, and it shows the specifics of what you're performing and what you're doing during that part of the phase, that mission mode. And then you could further break down, like perform lunar transfer into more and further down into more specifics of what's going on during lunar transfer. And even within that, like execute the translunar injection burn has additional functions that happens in each one of those. So for what you're doing at this point in your career, you probably don't need to go down to level 4 and 5. But I think it is important that you understand this process, because this is used by a lot of the aerospace companies. It's actually used, by NASA and a lot of the other industries, but also can be used for many other things. Even designing a car or designing a widget of any type, you look at and understand what is the functions this widget needs to perform. So here's some examples of major functionalities. Provide pressurized habitable volume for crew and equipment. So basically that's saying that function is provide a pressurized capability. So functions lead to capabilities. So you're providing a capability that can be launched within TBD, transferred by Orion to a destination, sustain operational lifetime 15 years. So that's the capability of that function. So provide life support, and you can read here through the capabilities, basic capabilities for TBD, and it's okay to have TBD day descriptions of what it is, because you may not know how many days yet of your mission. You should know, but you may not know. But you can walk through here, and these are kind of typical functions. Provide life support, provide support to the crew in space, provide docking capabilities, receive and provide interfaces from resources, a robotic arm, internal and external science and imagery. So you can see how you can walk through this and better understand each of the functions and what those capabilities might be that you need to perform that function. Here's some examples already done for you in relation to exploration habitat functionality. So you've got the discipline and the functional title. So you've got structures, mechanisms, power, thermal, ECLSS, fire safety, crew systems, avionics, comm, guidance, navigation, control, if it's applicable, imagery, EVA, science, and robotics. And each one of those have some additional functional decomposition titles. So this can be helpful. Keep this in mind because this is already basically done for you. It's a checklist, if you will. If you're looking at exploration habitats, you can go through here and look at, provide power. What does that mean? That means provide power distribution, storage, management, quality, control, and conversion. What it did not have here is power generation. It was assumed that was separate, but power generation would be a part of that as well if that's included on that spacecraft or interplanetary spacecraft. Here's some additional functions, further breaks down ECLSS into specifics, such as, cabin air particulate control. So this, you would think of, just put a provide in front of these, provide cabin air, cabin carbon dioxide removal. Here's a gateway example of functional summary. You've got cislunar power and propulsion bus, which it has these functions. You've got the habitat mission kit, which provides these functions. And then you have the Orion, which actually provides functions while it's docked to the stack. So when you have the Orion docked, you can take advantage of some of its capabilities, its functionality, to supplement the overall functionality of the system. So here's some additional, so when they add an additional habitat, Habitat 2, you've got additional functionality. So they added a galley, crew quarters, and a toilet. So you can see how this does add additional functionality. In the previous version, the Orion, actually it should be in here, waste collection, it is toilet. So they do have the waste collection, and the assumption there was that while Orion is docked and humans are here, human tended, that they would use the Orion facility and not necessarily have an additional toilet. But when you get into longer capability, longer duration, then or crew staying on board while the Orion leaves, then you do have that functionality. In most cases, crew will never be on here without a capability to escape or safe haven to leave. So you'll always have some type of vehicle, transfer vehicle, Orion or otherwise, to leave the station. So here's kind of a map of functions to product structure. And so this looks at how to allocate functions to elements. So you have your list of all those functions, and then you begin to look at your products, your different segments, your different elements, your different subsystems, and so on. And you begin to map all those functions down the left side to all the different elements that are part of the system. And then once you have that and understand that, you can begin to write your functional requirements and then also your performance requirements. And remember the difference between functional requirements and performance requirements. So now I want to talk about requirements definition. Let's talk more about the details and what it means to define requirements. How does NASA use these requirements? Well, they use them in a lot of ways. They're used in policy documents as part of the process. They're used in statements of work, the tasks to be done. They're used in program and project documents at a high level, level 0, level 1, level 2. They're used in standards, best practices, the NASA Standard 3000, Volume 1 and Volume 2. Volume 2 is about habitability and human factors and things of that nature. So that standard becomes requirement inputs. And they're also used, of course, as end item specification, the design to and the build to specifications for development and manufacturing integration of these systems. Important aspect about the terminology of requirements is a shall is a requirement, it is binding. Will is more of a fact or a declaration of purpose. It is not a binding requirement, it's not a shall. And should is a goal. It's not mandatory. So when you see these three words in a requirement statement, keep in mind that shall is a requirement, will is fact or declaration, and should is a goal, but not mandatory. Characteristics of a requirement is it must be verifiable. The provider can show concrete evidence that the requirement has been met. So the hardware and software that has been built can show that they've done the verification analysis or verification of the system of that particular element or components or whatever it might be, and that it meets that requirement. It should be clear, one thought, unambiguous. It should basically be one sentence, two at the most, but oftentimes when I was working requirements, I would go through and scrub requirements because I could find that there was more than one requirement within a statement. So you want to break those apart, two separate requirements. Don't combine them together. Keep them separate. Keep them very simple and one thought. And you want to state them positively. You want to say they shall do this or they shall perform this. You don't want to say they shall not do something, because how do you verify that? So requirements in context. There's lots of different aspects of requirements, as we just stated. There's stakeholder expectation requirements. There's high level requirements, needs, goals, and objectives, operational requirements, operational test objectives or mission objectives that further break it down. And then you have your product breakdown structure, the allocation of those requirements, concept of operations bring in additional requirements, your functional analysis bring in requirements. So all of this activity comes together to define the requirements. And there are derived requirements and allocated requirements. A lot of the allocated requirements come from above. The derived requirements come from analysis and studies of the mission and the systems and the elements. And they can be functional, performance, interface, operations, and ilities. Ilities being maintainability, serviceability, these kinds of things. So these are important requirements. Getting all of this is a big job, and you need to document everything about it. And when you're documenting requirements, you want to document so you have your requirement statement, which is a one sentence, simple, straightforward statement. Then you have a paragraph below that is what you intended this requirement to be. So it's an explanation of the requirement. The other aspect is, and below that, you put in the verification and verification of that requirement. How do you intend to verify it? By inspection, by analysis, by testing, what? So here's the kind of the requirements definition process. You have your inputs that come from your stakeholders, configuration management, and then you begin to analyze the scope of the problem. You define the design and product constraints. You define the functional behavior expectations, or in terms of technical. Then you define the performance requirements for each as defined by the functional and behavior expectations. From that, you define the technical requirements in acceptable shall statements. And then you validate technical requirements. Remember the difference between validate and verify. You validate against the concept of operations. Is that function needed, required in order to implement these test objectives, the mission objectives, et cetera. And you define the measures of performance for each of these from a standpoint of measure of effectiveness. You establish a technical requirements baseline, you define a technical performance measures, and you capture all that knowledge in the documentation. So the outputs become validated technical requirements, measures of performance, and technical performance measures. Here's another view of that requirements flow down. The difference being this shows how it breaks down into a system level with all the inputs and additional constraints put on by environmental constraints, other design constraints such as manufacturability, quality control, and other guidelines such as or standards such as the NASA Standard 3001. And so once you document all that, that is your system performance level, and then you break it down into, and this could be at an element level, element to element, or system, and then your subsystems, and then you keep breaking that all the way down. So there's requirements can be kind of challenging, and there's a lot going on that influence requirements and to get them right. So you've got the flow, the type, and the ownership. And so you have the aspect of the program requirements, which are mission directorate imposed requirements, self-imposed derived requirements from analysis and studies. And those flow into your project requirements. So that's for the program imposed requirements on the projects. So a program could be Artemis, and the project could be the specific lander, or the crew cabin, or even the surface transportation, which is, you know, a rover. So from that, you've got the interrelationship of the type. You got programmatic requirements, you got the functional requirements, you got the programmatic requirements and technical requirements, which is your functional and performance requirements. Those functional performance requirements are owned by the program and project, and then the technical requirements, part of those technical requirements are owned by the technical authority. So a part of this is the technical authorities from a NASA perspective oversee a lot of these requirements and have insight to make sure nothing's missed. So you have the Office of Chief and Health Medical Officer, a technical authority. You have the Engineering Technical Authority, and others. You have the Safety, Office of Safety and Mission Assurance Technical Authority. So this talks about level 0, level 1 requirements, the high level requirements. So you have your top level requirements, such as transport, deliver, and return for crew to and from the ISS. This could be your commercial crew requirements. And this shows over here the idea what I was talking about. You have your requirement. It's a one. This is the exploration architecture requirements. The exploration architecture shall deliver crew and cargo to the ISS and return them safely to Earth. So you can see how that's a shall, and you can verify that. So here's the rationale, which I talked about. What's missing is the verification statement should also be included. So you have rationale and a verification statement that supports this statement. And it's important to have the rationale because if you leave some requirements, if they're vague or really don't have a clear definition to them, they can be interpreted by the contractors or the vendors in different ways. And so having this rationale really helps to explain the intent of the requirement if it's not super clear. So there's other aspects like the human system requirements. Like I was talking about, the Human Health Performance Standard 3001, that also are additional requirements that influence and are put upon the list of requirements for that system. Some directly come from needs, goals, and objectives, which is important, why we discuss that and talk about that. And then there's agency controlled detailed requirements, things like exploration mission reliability, you know, loss of mission, loss of crew, etc. These types of expectations of performance requirements. Level 2 is that next level down, really decomposing level 1 requirements. They define the integrated segment and major elements and interfaces. They define the overarching functional and performance requirements and enough detail to be able to allocate to level 3. So as an example, here's the one: Orion shall return the crew and cargo from lunar rendezvous orbit to Earth's surface. And then here's how the applicable design reference mission that is a part of this, which is your concept of operation and the rationale behind that. The level 3 requirements are really are about focused on the major elements or the project, such as the Orion or the lander or the interplanetary spacecraft. The attention is on a contracting approach, which you're looking for vendors to then build this. So think of these as your build to specs. Orion is standard government contract, commercial crew, higher level. So the commercial crew requirements, they tried to leave at a higher level in the sense of requirements to allow more flexibility and more creativeness from the contractors. However, having worked commercial crew program for a short time, we ran into several aspects that delayed the commercial crew program because the way the contractors interpreted it would have been harmful to the crew upon return through the atmosphere and from a physical standpoint. And so we, where we had left that some flexibility, both contractors interpreted it a little bit differently, and we had to go in and clarify, which costs us time and schedule, and it also costs us budget. So the Lunar Orbital Gateway is commercial approaches and strategies mixed with international partners. So verification and validation testing, we were talking about this a few minutes ago, a difference between verification and validation. And I went through this before, but I want to touch on it again. So testing is a detailed evaluation method of both verification and validation. And verification versus validation objectives are different. Verification testing is really linked to approved requirements, such as the system requirements document, and can be performed at different stages in the product lifecycle. So verification shows proof of compliance with that requirement, that the product that meets the shall statement as proven through either a test, analysis, inspection, or demonstration, or any combination of those. And so you want to, when you do your verification test, because they are the official for record testing, you want to make sure it's documented well and captured, because that will go into your records that give you certification of the flight unit. And then those verifications tests are instrumentations and measurements that are generally accomplished by engineers, technicians, operator, test personnel. Validation testing is a bit different. Validation of a product shows the product accomplishes the intended purpose of that intent in the intended environment, that it meets the expectations of the customer and other stakeholders as shown through performance of a test, analysis, inspection, or demonstration. So you validate that you have the right requirement, or you have right function, or the concept of operation. So the validation does relate back to the concept of operations, that indeed the validation ensures the system is operating as expected when placed in a realistic environment. So here's the systems engineer's dilemma of system balance. At each cost-effective solution, you're looking to here's your dilemma. To reduce cost at a constant risk, performance must be reduced. To reduce risk at a constant cost, performance must be reduced. To reduce cost at a constant performance, higher risk must be accepted. To reduce risk at a constant performance, a higher cost must be accepted. So in this context, time in the schedule is often a critical resource. So that schedule behaves kind of like a cost. So you try to balance these three things, but at some point you're going to have to give more credence to 2 out of these 3 items. So that concludes my discussion today, my lecture pertaining to functional decomposition and requirements. It gives you a brief overview of what they are and how they're used. Thank you.